Hi, I'm Jake.
I'm Vince,
I'm Bud.
And I'm Brendan.
and for our feedback control systems final project, we decided to do an autonomous vehicle. According to a tri-level study on the causes of traffic accidents, 90 to 93% of all traffic incidents were caused by human errors or deficiencies. Having a completely autonomous vehicle would not only make the roads safer, but also would save massive amounts of time. The average person drives approximately 101 minutes per day, and this equates to approximately 50 hours per month. These are the two main reasons why we decided to pick an autonomous vehicle. As you can see here, this is a visual description of our model. This is our car here, mounted with a proximity sensor in the front to measure the distance between the front of our car and the back of the vehicle that we're following. Also, a few other things to note on this diagram here are the drag and the friction from the wheels of the car. Here is a simplified plant model for our system. The M blocks stands for the mass of our vehicle. The B block is representative of all the damping forces such as drag forces and the friction forces that were on the previous picture. For our model, we have a force as an input for our motor of our vehicle, and we have X as the distance for the output.
Okay, so here we have our transfer function. This is the position over the force, our input over our output for our plant model. This is the equation that represents our plant model. Here we have 1,500 kilograms as the mass of our vehicle, which is about the average mass for a sedan. Here we have 0.5 as our dampening coefficient. This represents the wind drag force as well as friction of the rolling friction from the tires. We decided upon this 0.5 using a reputable source, Engineering Explained. They talk about a lot of different engineering and physical phenomena of these types. Here we have our performance goals. Our input is that we want our car to follow the car in front of it at about 50 meters. We wanted our steady state error to be 0, which means after an infinite amount of time, we want our car to be following the car in front of it at exactly 50 meters. We wanted a rise time of less than or equal to 1 second, which we decided was a good value and used University of Iowa as a source. This is just the amount of time that our car needs to adjust to the velocity of the car in front of it. And then a percent overshoot of less than 10%, which means that if the car in front of us were to speed up a little bit and we had to catch up, that we wouldn't be getting any closer than 45 meters to that car, which we decided was still following a safe distance. Here we have the response to an open loop, or the response to a step input. If you look at the position versus time, you can see that our position will go to infinity and there is no boundary on that. However, our velocity will taper off and top out at about 60 meters per second. This is due to the forces acting against the vehicle, such as drag and friction.
So here we have a very simplified block diagram of our system in general. As we can see, we have an input, which is the desired distance of 50 meters. And then all the way at the end is y of s value is our actual distance that we are from the car in front of us. Now this is more of a traditional feedback style loop, as you can see. We're coming all the way around from our actual value, and this here is going to be the data sort of measured by the sensor, the proximity sensor that is. Comes all the way up to the top. Now this is where the data measured by the proximity sensor is actually processed. So we see here that the controller is going to be a multiplicative value that's going to adjust that and sort of get us closer and bridge the gap between our actual distance and the required distance or the expected distance that we sort of want. And that multiplicative factor is going to affect, our plant model in general there. So as we can see here, we do have a truck position input, and that can be anything from a sinusoidal to a ramp input, really anything that the vehicle in front of us is going to do. Now, this kind of gets us on the topic of why feedback is so important, and it is really just for this reason. Without feedback, we wouldn't be able to tell how we need to adjust to get closer to our desired value. So it's sort of, looking at what we have and seeing what we can do to get closer to what we need. And that's sort of the science of feedback control systems in general. Here we have the Bode diagram of our project, essentially. This is just up to basically show that our steady state error does go to 0. Now, if we look at this logarithmic scale, all the way to the left here off the screen, we have 0, right? And since it's logarithmic, it's going to be way over there. At that point, this magnitude value is going to be all the way up at infinity, Now, if we look at our steady state error equation, it's going to be 1 over 1 plus the magnitude value at a frequency of 0. And as we just talked about, that value is going to be infinity. 1 over infinity gives us 0 steady state error. Now, this was our first attempt at tuning our model in general. We were trying to use just a regular old P-type controller, and we soon found that this wasn't going to be suitable for our sort of requirements and needs. When we look here at the root locus editor, we see that our poles are essentially on the left-hand plane, which is stable, but they're not in this white region, so they're not meeting our design requirements of the 10% overshoot. This value here, where this sort of cuts off and the yellow turns over to white, that's also sort of indicative of our settling time, or essentially how fast the value gets to where it needs to be. And again, our poles were not within that value, so we did have to end up adjusting, and we moved over to a PD controller, and that's what we'll be implementing next.
So once we found out that a proportional controller wouldn't work, we took our open loop plant model into CISO tools and decided to try some other things. Originally, we saw that our Bode diagram looked something like this and that our steady state error was driven to 0. So the next thing to worry about were rise time and percent overshoot. So two very important values for these are that we can find on the Bode plot are phase margin and the crossover frequency. And those are shown right here. We ended up having to implement a 0 into our controller and then adjusting the K value accordingly. We wanted these values, phase margin, to be above 79.6%, and we wanted our crossover frequency to be above 2.2 radians per second. And as you can see, we were finally able to achieve those two values, meaning that our design requirements should be met. Here's another root locus diagram, this time implementing the PD controller. And we can see that all of our poles are still to the left of the imaginary axis, meaning that our closed loop system will be stable. Also, as we crank the gain, we can see that the poles will follow along these blue lines and this blue line, and we end up getting all of our poles inside the white area, meaning that all of our design requirements are met. So once we implemented this new controller with the derivative, we plotted it on MATLAB, and this is the step response to our unit input of 50 meters. We see that there's a rise time of 0.38 seconds, which is really good, and then our percent overshoot is just under 10%. So CISO Tools was kind enough to give us this formula for our controller. We can see that it requires a derivative here, 1 plus 1.5s, and then this K value of 4,242. This is rather high, and we see that as we take this system and take it from the frequency domain back into the time domain, it's kind of an unrealistic expectation to put on our car's motor in terms of horsepower. So moving forward, that would be one thing we need to kind of make more realistic in this design. Also, going back to the sensor that Bud talked about, and our closed loop feedback, in our feedback loop, it was assumed to have a value of 1 which would be an ideal sensor with no time delay or any imperfections, and that is obviously not possible. So in terms of implementing this autonomous vehicle, we would also have to evaluate imperfections in the motion sensor and find out time delay and how much time delay could be tolerated and stuff like that.